validate the history behind the understanding of light as photon and matter waves and its duality with all the different assumptions of light made by different scientists. Introduction. The Maxwell's equation of electromagnetism and Hertz's experiment on generation and detection of electromagnetic waves established the wave nature of light in 1887. The discoveries of photoelectric effect by Hertz, Compton effect by Compton established the particle nature of light. Hence, it was concluded that light has dual nature. Lasers are used everywhere from concert light shows to grocery store. Photoelectric effect. Hertz observation. The phenomenon of photoelectric emission was discovered in 1887 by Heinrich Hertz during his electromagnetic wave experiments. In his experimental investigation on the production of electromagnetic waves by means of a spark discharge, Hertz observed that high voltage sparks across the detector loop were enhanced when the emitter plate was illuminated by ultraviolet light from an arc lamp. Light shining on the metal surface somehow facilitated the escape of free and charged particles which we now know as electrons. When light falls on a metal surface, some electrons near the surface absorb enough energy from the incident radiation to overcome the attraction of positive ions in the material of the surface. After gaining sufficient energy from the incident light, the electrons escape from the surface of the metal into the surrounding. The next one is Lenard's observation. Lenard observed that when ultraviolet radiation was allowed to fall on the emitter plate of an evacuated glass tube enclosing two electrodes, current flows. As soon as the ultraviolet radiation was stopped, the current flows also stopped. These observations indicate that when ultraviolet radiations fall on the emitter plate, electrons are ejected from it, which are attracted towards the positive plate by the electric field. Particle nature of light, the photon. Einstein arrived at important result that the light quantum can also be associated with momentum hv by c. A definite value of energy as well as momentum is a strong sign that the light quantum can be associated with a particle. This particle was later named photon. The particle-like behavior of light was further confirmed in 1924 by the experiment of A. H. Compton on scattering of X-rays from electrons. In 1921, Einstein was awarded the Nobel Prize in Physics for his contribution to theoretical physics and the photoelectric effect. In 1923, Millikan was awarded the Nobel Prize in Physics for his work on the elementary charge of electricity and on the photoelectric effect. Characteristic properties of photon. In interaction of radiation with matter, radiation behaves as if it is made up of particles called photons. Each photon has energy E equal to hv and momentum P equal to hv by c and speed c, the speed of light. All photons of light of a particular frequency v or wavelength lambda have the same energy E equal to hc by lambda and momentum P is equal to hv by c equal to h by lambda. Whatever the intensity of radiation may be, by increasing the intensity of light of given wavelength, there is only an increase in the number of photons per second crossing a given area, with each photon having the same energy. Thus, photon energy is independent of intensity of radiation. Photons are electrically neutral and are not deflected by electric field and magnetic fields. In a photon-particle collision, such as photon-electron, the total energy and total momentum are conserved. However, the number of photons may not be conserved in a collision. The photon may be absorbed or a new photon may be created. Experimental study of photoelectric effect. The apparatus consists of an evacuated glass or quartz tube which encloses a photosensitive plate C. A transparent quartz window is sealed onto the glass tube which permits ultraviolet radiation to pass through it and eradicate the photosensitive plate C. The electrons are emitted by the plate C and are collected by plate A. When the collected plate A is positive with respect to the emitter plate C, the electrons are attracted to it and hence photoelectron current is constituted. Einstein's photoelectric equation. Energy quantum of radiation. In 1905, Albert Einstein proposed a radically new picture of electromagnetic radiation to explain photoelectric effect. In this picture, photoelectric emission does not take place by continuous absorption of energy from radiation. Radiation energy is built up of discrete units, the so-called quanta of energy of radiation. Each quantum of radiant energy has energy Hn, where H is Planck's constant and n the frequency of light. Dual nature of radiation. Wave theory of electromagnetic radiations explain the phenomenon of interference, diffraction, and polarization of light. On the other hand, quantum theory of electromagnetic radiations successfully explain the photoelectric effect. Compton effect, blackbody radiation, X-ray spectra, etc. It means radiation sometimes behave as a wave and sometimes as a particle. Therefore, Louis Victor de Broglie suggested the particles like electrons, protons, neutrons, etc. have dual nature, that they can have particle and wave nature. Next, Davison and Germer experiment. The wave nature of electrons was first experimentally verified independently by C. J. Davison and L. H. Germer in 1927 and by G. P. Thomson in 1928 while observing diffraction effects with beams of electrons scattered by crystals. The experimental arrangement is schematically shown in the figure. This one. And it has an electron gun made up of a tungsten filament F heated by a low voltage battery, and the filament is coated with barium oxide. Emitted electrons from filament are accelerated to a desired velocity by applying the required potential or voltage from a high voltage power supply. C is a hollow metallic cylinder with a hole along the axis and is kept at a negative potential to get a convergent beam of electrons emitted from the filament. It acts as a cathode. A is a cylinder with a fine hole along its axis acting as an anode. The cathode and anode form an electron gun by which a fine beam of electrons can be obtained at different velocities by applying different accelerating potentials. N is a nickel crystal cut along a cubical diagonal, and D is an electron detector that can be rotated on a circular scale and is connected to a sensitive galvanometer that records the current. Working of this experiment. From the electron gun, a fine beam of accelerated electrons is made to fall normally on the surface of the nickel crystal. The atoms of the crystal scatter the incident electrons in different directions. The detector detects the intensity of the electron beam scattered in a particular direction by rotating the electron detector on the particular scale at different positions. And next one, de Broglie hypothesis. In 1923, Louis de Broglie combined work done by Einstein which described the relationship between mass and energy in matter, and work by Max Planck which described the energy in a photon wave into one relationship under the hypothesis that matter could also behave like a wave. This is usually called the de Broglie hypothesis. In classical physics, particles and waves were separate, well-defined entities. Particles are described as localized objects that have a definite boundary of existence. All particles have physical properties like volume and mass. Waves, on the other hand, are a disturbance of another physical medium like a sound wave that propagates through the atmosphere. All waves have an associated frequency which is defined as the number of times the wave goes through a cycle in a given time, usually measured in hertz. This is typically measured by counting the times a peak passes through a specific location over a unit of time. Waves with different frequencies is shown in this picture, and However, inconsistencies in classical physics started to arise in the late 19th century, which led to Einstein to make his claim about light acting like a particle. The photoelectric effect describes how light interacts with electrons, and the numbers were not lining up with classical mechanics. However, if light was treated as a particle, that's something that can hold a specific quantity of energy in a defined space, the data made sense. And in the de Broglie hypothesis, this was applied to matter and not just light. So, on an atomic scale, particles like electron would hypothetically act like waves in that they do not have defined boundaries or a set location in the way we think of particles. In conclusion, the concept of the dual nature of radiation and matter has completely transformed our understanding of physical world. It has shown that both radiation such as light and matter, like electrons and other particles, can exhibit characteristics of both particles and waves. This duality was first proposed by scientists like Max Planck and Albert Einstein, and it was further developed by Louis de Broglie and others. Through various experiments such as the photoelectric effect and electron diffraction, we have observed phenomena that can only be explained by considering the particle-like and wave-like properties of radiation and matter.